Hey guys, welcome to the class. So today we're gonna try to progress on this very long chapter. This is, I think, the longest chapter of the whole class. And in particular, we're still dealing with a consumer problem, and we have introduced this expenditure minimization problem, and we're gonna summarize it today, right? So the summary of the relation between the expenditure minimization problem and the utility maximization problem. As you remember, the expenditure function, right, is this minimum value for a given utility of how much the consumer will spend to attain that level of utility, right? And this is captured by the product of the prices, which is a vector, remember, and this is the inner product, hence a transpose times the Hicksian demand. And you remember, again, the Hicksian demand is a vector L times 1, right, for a fixed price, L is a vector value function. And here we're fixing U. So one important thing about this chapter is we have worked basically with fixed U all the time. Now we're gonna play a little bit with this value of U, making it a variable and in fact sometimes a function. And we're gonna use this to connect the expenditure minimization problem with the utility maximization problem, okay? As someone of you pointed out, this is the famous duality theory between the EMP and the UMP. So one historical point, so when people were working about how to best describe the consumer behavior, there were two approaches, right? One done by Hicks, that was basically with the idea that people do not maximize utility, they minimize expenditure, right? For a given utility. And there was another branch, basically thinking of utility maximization, which you may remember from your history of econ, if any. Sometimes you don't have that class anymore. The marginality revolution, right? With one of them being Vilfredo Pareto, right? Italian economist. So Vilfredo Pareto was one of the most complete treatments, right? And he basically was one to formalize the utility maximization problem, right? So, initially these were two branches, very different, opposing almost views of how to best describe consumer behavior. As things happens, the people that know a little bit about Hegel, right? And we have, thesis, antithesis, and then synthesis, right? So you can think of this a little bit as the synthesis of those two approaches to consumer behavior. And of course, I always tell you this theory, we invest as economists lots of time on this, and very smart people work on this. So you can see this almost a very, later stage theory. So it's very consolidated, very solid, and of course, a lot of synthesis. So these are the two branches that now you see as this little part, a summary of EMP and UMP. So a lot of back and forth, right? And people were thinking these things were distinct. They are not, right? They are just two faces of the same coin. So the first part is essentially the relation between the Hicksian demand, by Hicks, and the famous Marshallian, then expanded and formalized by Pareto mainly, XPW. And the way they relate to each other is by basically changing the U bar that before was a value. We now change that value by the value of the indirect utility evaluated at P and W, the income level. So as you can imagine, what was that object? The indirect utility. So what was indirect utility? The optimal value of the UMP, right? So if I replace the optimal value of the UMP inside the target level of the Hicksian demand for the same prices, I get out the Marshallian demand, right? So XPW. So essentially, this provides a way to use the Hicksian demand to go to the Marshallian demand. Now, importantly, right, what is the key issue with the Hicksian demand? The Hicksian demand, as I mentioned in the previous lecture, is that it is not observable, right? Can you realize that? Essentially, you cannot see U, at least now with the current data sets, right? Now we have NeuroEcon, probably we'll have our Neuralink here, right? So observability of utility is something that is not currently, doable. But given the data sets we are studying, it's not observable. Hence, the way to make it observable is basically to think of this duality using the indirect utility. Second relation, say now I have the observable, in principle, Marshallian demand, and now I want to obtain the Hicksian. So a little bit, a very fair question you would ask me is, okay, so if you did a theory and you spend a class thinking about EMP and then it's not observable, why do we do it, right? So that's a very fair question. And the reason is that because of this duality, we can actually go back and forth. So, essentially what you will do is you will estimate, using metrics and econometrics, you will estimate the one that is observable, the Marshallian demand, right? And once you have done it, right, then you will essentially be able to obtain, if rational, right? You will be able to obtain, and this is something we'll work today by a process called integrability, right? The utility function behind the Marshallian demand, right? If rational. And once you have done it with the utility function, now you can solve the EMP, right? And if you solve the EMP, now you can obtain the expenditure function. So using the expenditure function, now you can replace it back and do this. X P, comma, instead of income, you replace it by the expenditure function, evaluated at the same price, importantly, and at the level of target utility you want. This will give you back the Higgsing at that same price level and at the utility you are fixing on the expenditure, right? Okay, great. So now we can go back and forth between Marshallian and Higgsing demand, right? Synthesis. But now, in the end, there is something more important. Of course, the demands are in the end our object of interest, but we still have to deal with the main point of duality, that is that the indirect utility and the expenditure functions are inverse functions of each other, right? So in other words, right, so as you can see here, right, the indirect utility is the inverse of the expenditure. That is what the first line is saying, that I'm highlighting now. So for all of this, remember that inverses are very easy to understand from one variable. So when you have functions of one variable, what is an inverse, right? It's basically a map that I apply to the original map, right? Usually is denoted by f minus 1, right? If my original mapping was f. And if I apply f minus 1 to f, I will obtain the identity, right? The argument of the function. That's broadly inverse mapping. Now, if you have multivariate functions, right? Having an inverse is more complex. Do you understand that, right? So when you have more than one variable, inverses are way more complicated. So here we are going to fix prices, and we're only going to think about the inverse for a fixed price. Understood? Okay. So prices are fixed in this part. They don't move. So the inversion that we're talking about is in terms of the second argument, which is, in this case, income, right? So you take essentially, the expenditure, right? Which for fixed price, for a given U, the argument is a U, right? And now I basically apply the indirect utility to it. So now it's indirect utility, price are fixed, right? So it's only in the second argument, which is moving. I apply to the expenditure, and what I get back is the utility, right? So it's exactly the operation I described. This is an inversion. So that means that for fixed price, the V function, the indirect utility, is the inverse of the E function, the expenditure function. Understood? Okay. Now, that's a cool thing. You're more advanced students, so you know that an inverse, maybe to the left, to the right, this inversion may happen in one direction, not in other. Luckily for us, in this particular case, this is a full inverse, right? So there is a bijection between the two. In fact, I can actually take now the expenditure function and notice this is also an inverse of the function, right? That's nice to have. In particular, now if I apply for fixed price, the expenditure, I apply it to the indirect utility in the sense that instead of having the U bar, I now evaluated at the indirect utility at PW. Remember the P is fixed and W is changing. I get back the W, okay? So in other words, the expenditure is the inverse of the other, perfect, it works. This is the important part of this section. So expenditure and indirect utility are inverses of each other for fixed price, and hence I can use them to be able to go back and forth between the Marshallian demand and the Higgsian demand. Okay, great. Now, that's a nice thing to have, right? It's, of course, aesthetically pleasing, but it's going to be useful. And the main reason and the zenith of this chapter essentially is that we're going to use all the very nice properties of the Higgsy demand we derived the previous lecture, remember? So who remembers this? There was a substitution matrix, which was, the Jacobian of the Higgsian. So matrix L times L that I told you to think about and refresh any calculus, the little concepts that I told you to check, right? And this substitution matrix or Jacobian was nice because it turns out that due to the envelopes theorem, Shepard's lemma, this thing was a Hessian of the expenditure. So just to remind you, we have these 4 properties in proposition 15 that basically told me that the substitution matrix was, first of all, symmetric, right? It was negative semi-definite, that we also remember what was a negative semi-definite matrix. And on top was homogeneous of degree 0, okay? So that means it has 3 really cool properties, but all these properties are a little bit here uninteresting because they come from something unobservable. Using duality, we're gonna use it now to study a new object, which is more interesting and people actually can see it and estimate from data. And this object is the Slutsky equation, okay? So Slutsky was a Russian economist. He was other of the first formalizers of microtheory. These guys took the Vilfredo Pareto ideas even deeper, right? And, he basically proposed the following object that it was in the chapter 2, but I'm gonna introduce it here for just having comprehensive and fully autonomous lecture, right? So the Zlotowski matrix, first of all, is a mapping, right? From prices and income to basically the following object, right? So matrices of size L times L, okay? I think, yeah. You understand the notation, right? So these are matrices of size L times L. And then what are the classical, what is essentially, let me see which particular notation I'm using. Yeah, I'm using capital S. So for a given price and income, what is the LK entry? So this in particular is going to be, it's going to have 2 components. It's going to have the partial derivative with respect to price K of the quantity L, right? Of the Marshallian demand. And then, it's going to have also, so sorry, here I have to use PK because there is also income, okay? And also it's going to have the partial with respect to income of XL PW, right? Times the quantity XK. Okay, so this is entry LK of the Zlotowski matrix, right? And now I can also write it in the following way. So it's going to be SPW, it's going to be the Jacobian of the XPW with respect to prices, right? And this is basically, in fact, you can also write it as a gradient, but in this case, a Jacobian is more general than the gradient, so it's going to be the Jacobian with respect to income, right, which we know is a vector of the XPW, right? And then I'm going to have here XPW transpose. So it's an outer product, right? So remember that this thing here, because the demand is a vector and it's with respect to a scalar object, right, is of size L times 1. And the quantity is just a size, of course, L times 1. So I have to do, this is called an outer product as opposed to the inner product. So this is going to produce a matrix of L times L, right? So when the transpose is at the end, so to speak, right? Basically what you're doing is taking 2 vectors and exploding them into a L times L matrix, right? Do you understand the dimensions? So this object here is L times 1, right? And this object here, once it's transposed, right, is 1 times L, right? So when you multiply these objects, it's going to be the outer product, right? So L times L, okay? Understood? Okay. Yeah, so this is the object. I have provided the 2 descriptions, entry-wise and the matrix description. One important thing is the following, right? Is that I want you to realize that this is a little bit similar to the substitution matrix of the Higgsy, right? But there is an additional term, and this term here is sort of a weird term, right? It's basically income effects, but multiplied by the quantity, right? And in particular, you know, this object is the object we're going to try to make sense, because we're going to claim this object is the object of interest to do comparative and comparative statics for the Marshallian demand. So the important thing, and you remember this from now on, is that when you're trying to do comparative statics in the world of utility maximization, there is a bit of an issue, right? Because if you try to just see how the basically demand changes as prices change, I have to take into account that, you know, there is a budget constraint, right? So when prices change, I'm changing the constraint, right? And this creates issues, right? So forget about this for a second, and let's go back a little bit to the EMP. And remember what's happening in the EMP. So in the EMP, I'm fixing the utility, right? So what I'm essentially doing is fixing, you know, the level of target utility I want the consumer to achieve. And then I'm asking how the demand or the Higgsian demand will change in quantities with respect to changes in prices. And this is a cool analysis, right? Because in doing this, I'm fixing always the level of utility, right? So in this sense, this is a very cool comparative statics, because I'm asking how demand is going to change as price changes while keeping utility fixed, right? So this is a very neat comparative static analysis, because I'm keeping constant welfare and I'm allowing price changes, and then I'm observing quantity changes. So what I see is basically pure substitution patterns without, if you want, you know, changes in income, right? Changes in welfare, sorry, due to weird changes in income, right? So I'm going to explain this in another way, in another form. So imagine now that I don't have the expenditure function, and then I want to study comparative statics, right? In a way that makes sense. In other words, I have to basically take into account that if I change a price, right, I can not only study the partial derivative, right? Because changing prices also changes what is affordable. Do you understand? Because price changes also your current affordability through the budget constraint. So I have to take that into account. So that means I have to do some sort of compensation. That's a keyword, compensation, right? So in order to do a proper analysis of price changes, I have to somehow correct your income changes such that they allow you to be able to afford whatever you were able to afford before my price change, right? And hence being able to guarantee that your level of welfare remains the same while changing the prices, right? Now, this is called Slutsky substitution, right? And I'm gonna do that right now, right? So imagine now that I take my price, sorry, I take my Marshallian demand, I take prices, and now I do the following. Instead of income, here I'm gonna consider the inner product of the given price times a quantity. Q is just a vector of quantities, right? And then I'm gonna take, right, and create my substitution matrix, right? So my substitution matrix is nothing else than a price, how my quantities are going to change with respect to prices, right? And this L times L matrix that we discussed, right? But now notice that in doing this operation, I'm keeping and I'm basically making sure that whatever the price, you can still buy the vector Q. Do you understand? So vector Q is a guaranteed commodity bundle or basket that you will be able to afford irrespective of the price change. Do you understand? This is an Slutsky substitution, right? That allows me to buy a Q, okay? Now I see the price change, and here I'm just gonna do chain rule, okay? So this dp xp p times q, sorry, plus, so how does the chain rule works here? Who can remind me? So first I do with respect to the first argument, right? And then I do with respect to the second argument, right? So dw x p, p times q, and then by the chain rule, right? This is q transpose, okay? Okay, good. Now, the Slutsky substitution is allowing me to always buy, irrespective of the price change, always Q, right? So in particular, it is a little bit loose in the sense that Q is an arbitrary commodity bundle, right? So in order to make something more sensible, I'm gonna choose Q to be the original price, the original commodity bundle that you were able to afford at the original price and at the original income. So base level, right? So let Q be equal to XPW, right? For the original price and income, right? And then replace to obtain a Slutsky matrix. Okay. So this means, right, that if I take this PW, right, I take it here and replace, essentially, I evaluate at Q XPW, right? This object is equal to the Slutsky matrix I just defined above. Okay, do you understand? So just check it out super quickly. Take the Q, make it XPW, Walras law holds, right? Everything works out, okay? Okay, of course. Remember that this is done under Walras law, right? So that means P times X is equal to income, okay? Understood? Everything checks out? Great. So now you know what is the Slutsky matrix. Now, and you know what is the Slutsky substitution. Basically, the Higksian substitution is the thing I just told you a moment ago, keeping the utility fixed. Now, what is the relation between Slutsky substitution, compensation, sorry, and Higksian compensation, and hence between the substitution matrix of the Higksian demand and the Slutsky matrix. And the relation is the following. So take now the substitution matrix of the Higksian, right? And then just write down using the duality that we just wrote in the summary of the relation between EMP and UMP. By using the duality, right, turns out that I essentially get the following, right? I get that the first part is the partial derivative of X, right? Because remember that the Higksian, as I wrote it here, right? Look at this relation. So I'm just gonna copy it, right? So, I have it here, sorry. So now we have, of course, the Higksian is equal to the Marshallian evaluated at expenditure function. So now take the Higksian and take the substitution matrix, okay? Now I do a similar operation to before. So this is using the chain rule. So the first part of the chain rule is just the substitution matrix of the Marshallian. Great. Plus the income effects of the Marshallian, and then the derivative of the expenditure. And what is the derivative of the expenditure? Is the gradient of the expenditure, right? That's chain rule. Now, apply Shepard's lemma. What is Shepard's lemma? Shepard's lemma told you that this thing here is the Higksian, right? Okay. Shepard's lemma tells me that this thing here, the gradient of the expenditure, is the Higksian. So it's the demand vector, okay? Now, put everything together and replace the utility by the indirect utility at a fixed level income, right, W. And now, by replacing at the same time, I obtain what is here? The Slutsky matrix, okay? Okay, and this equality of the substitution matrix of the Higksian evaluated at the indirect utility VPW and the Slutsky matrix of PW is what is called the Slutsky equation. Okay, and now, so we did all of this for what? So who remembers minutes ago, what were the properties of the substitution matrix of the Higksian? So that matrix F times L was, first of all, symmetric. So what is a symmetric matrix? Entry ij is equal to entry ji, right? That's symmetry. Second property was negative semi-definite, right? Okay, we described it, what was it last lecture. And finally, we also know that if I multiply it by prices to the right, it is equal to a zero vector, right? So in other words, is less than full rank, prices are an eigenvector of the associated to the eigenvalue zero, right? Many ways to see it, but in particular, you know, this is a geometric property of this matrix. So turns out that now, if I study the Slutsky matrix, which I can estimate from data, right? I can estimate a demand, and then I can differentiate it. I can compute the Slutsky matrix. The Slutsky matrix is an observable object. This, in principle, you can estimate it. This object here, right, turns out it has three properties. So these are testable implications of rationality in the world of linear budgets, the classical consumer theory environment. Okay, so now I have told you, right, that there are the implications of rationality in general are the weak axiom, right, of revealed preference, and also the generalized axiom of revealed preference, right? You remember this. Now I'm telling you that there are other implications when you study the Slutsky matrix. Of course, there's going to be a relation between the two. In fact, right, is really the difference going to be at what object are you looking at? So if you're looking at the derivatives, if you're looking at the Slutsky matrix, the implications of rationality are going to be this, that the Slutsky matrix is symmetric, negative semi-definite, and this homogeneity of degree zero property with the prices, right? That we're going to call from now on homogeneity of degree zero. And this is in fact what proposition 16 is telling me, right? Okay, everyone with me? So now we're going to do again empirical implications of rationality, but having a little bit of a different object. So instead of just seeing a finite collection of basically of observations of choices from menus, instead a data set, that we call it, right? Here we're going to see the substitution matrix, right? So all the patterns of change, basically differential patterns of change of quantities with respect to price changes. Okay, do you understand? Okay, and now let's read proposition 16. If a demand function, right, is a function, not a correspondence here, we're assuming also it's differentiable, right? So we can obtain the Slutsky matrix, is a function, single value. It's generated by maximizing rational preferences that are locally non-associated, subject to a linear budget constraint. Then the following happens. XPW satisfies Walras law, right? Is homogeneous of degree zero. We know that. Moreover, and this is the new part, its Slutsky matrix function, SPW, is for any PW, negative semi-definite, singular in prices, this multiplication with price equal to zero, and symmetric. That means that SPW is equal to SPW transpose, or that any entry ij is equal to entry ji. Okay. Now, what is the punchline of this chapter? It's going to be that these are, in fact, all the empirical implications of rationality or utility maximization. And in fact, if I have demand function, and then I'm able to check that its Slutsky matrix has these three properties I described, negative semi-definite, singular in prices, and symmetric, under Walras law, then in fact, I can use that demand to be able to get back the utility, right? Hence, this means these three properties are the necessary and sufficient empirical conditions that characterize rationality. So now, I'm going to say a sentence that's going to sound a little bit too high level, but you're going to understand it fully, hopefully by the end of the class. I'm basically going to tell you that these three properties of the Slutsky matrix, right, are the differential version of the generalized axiom of revealed preference, right? So I described the generalized axiom of revealed preference, and we're going to revisit it at the end of this class, right? And we're going to understand it in this context with linear budgets, with a Euclidean space of choices. So everything is going to come back to the chapter that we started our class, our course, right? But in between, we're going to get this study of the Slutsky matrix, which is a differential version, okay? Now, why this is nice or why this is useful? So again, this is a little bit historical. So because of how math works, right? Calculus was developed with Newton, right? So calculus is super old, right? Calculus is a math that has been with us scientists for a while, right? So that means, theories first try to understand the implications of rationality using calculus, right? And obviously we studied the substitution matrix, and then we find out that this Slutsky matrix is symmetric, negative, semi-definite, and of course with the singular in prices. You know, and this is very exciting. In fact, you know, Mascolel has a footnote, if you read his chapter, saying, you know, the symmetry of the Slutsky matrix is beyond what, you know, natural intuition will do. We need you know, mathematical economics to derive such intuition. You know, and if you think about it, it's actually a very weird property, right? Because think about what's happening. So let's go back to the definition of the Slutsky matrix. It's telling me the changes in prices of good L with respect to the differential change of price K, right? So imagine L is bread and K is butter, right? And then you have the income change of course, bread with respect to income multiplied by the quantity of bread. So even, you know, forget for a second about this term, you know, which is a weird term, but only think about this term, right? Imagine the income effects are zero, so that in fact, the income is fixed in every experiment you run. So you always fix it to 1. Even without that, you have this price change here with PK, you know, and then imagine now that you think of the opposite object. So you're now thinking of the entry, instead of LK, entry KL. And in that case, you're actually asking, what is the change in quantities of butter, so K, with respect to a price change of bread, PL? And then this Slutsky thing, you know, of course, with compensation, right, is asking this consumer to have symmetric substitution patterns, right? That the changes, compensated changes in quantities of bread when you change price of butter are the same than the compensated price changes of the opposite good, right? So this is a very weird property, right? In fact, it's surprising, to be frank. So when you started studying rationality, you're not thinking that you're going to get a substitution matrix, right? Differential behavior that is going to look like this. So you're going to get symmetry out of the blue, right? Somehow. Of course, we know it took years, centuries in order to synthesize our knowledge and find out this. This is the culmination of this discussion between expenditure minimization and, of course, utility maximization. And because of duality, right, now we discovered this substitution matrix is in fact symmetric, okay? So symmetry is really surprising. And also, if you think mathematically, it's very weird that a human, right, that is rational, coming from completeness and transitivity, now is translated into symmetry of substitution patterns, okay? So of course, when I was in grad school, I was actually amazed by this, and I love the footnote by Mascolel. I say, wow, so that means even Mascolel so far goes, and he says, you know, we still haven't been done with understanding this, right? So my professor at the time, Roberto Serrano, you know, he was a student of Mascolel and an advisee of Mascolel, in fact. And he told me, you know, even now we don't fully understand, you know, what it means to be symmetric. Of course, that's the theorist's mind, right? So we're very idealistic, try to really understand things deeply. That's really cool, you know? And I actually fell in love with that particular part of econ, right? But, you know, it is in fact a puzzle, right? Why, you know, human behavior that is rational may lead to this very weird geometric pattern, right? In the world of substitution. So as a footnote there, actually, I did my job market paper that got me a job here at Western, you know, on the Slutsky matrix, right? So actually my first paper was on the Slutsky matrix. So actually it took me to the rabbit hole, you know. So yeah, this thing is actually very cool. But at the same time, you know, as I have matured as a researcher, I noticed, right, that a lot of the interest on the Slutsky matrix and the fixation of symmetry, of course, came from the tools that we use, right, which were, of course, calculus. But now, as we have progressed in math, discrete math has become more and more important, right? And why is that? Because basically we're now using computers, right? And when you use a computer, you use algorithms, right? And one, for instance, previously, you know, macro was using differential equations, right? But now we use difference equations, right? Why do we use the discrete version? Because it's easier to implement in a computer, right? So discrete math has become more and more important. And so has happened in rationality statics. So now we actually have two versions of rationality implications, right? The discrete math version, which is the GARP, the generalized axiom-Bernoulli preference, and the continuous version, right? The smooth version, the calculus version, which is the Slutsky matrix. So they are one and the same. And it took me, you know, years to understand the connections between them, right? But, you know, this is essentially, you know, interesting how our tools in math, you know, color how we understand a concept, right? And for me, in the end, symmetry actually is still a bit of a mystery, because it's something that if you have finite data and experiments, actually you can never test, right? So symmetry is not testable. It's a very weird object. But the combination of symmetry and negative semi-definiteness, right? They are one and the same with this very easy to understand property, the generalized axiom of revealed preference, that revealed preferences relations are not acyclic, right? So that you rule out acyclicity. So you can think of symmetry as this differential version of lack of cycles, right? And in fact, there is something, a study by Richter and Beal, called the Beal cycles, where basically say that symmetry of the Zlotowski matrix is equivalent to the lack of cycles in a form of compensation, okay? So this is a little bit too deep, is a subject of second year, and of course the Joe Mark paper, which I went to my own rabbit hole. So you can choose your own, right? I took that one for me, but basically I really went into that and tried to understand this. But for you, what you have to understand at this particular stage is that symmetry and negative semi-definiteness are this differential version of these connections of revealed preference relations. So inside this, when you see patterns of substitution in an object such as the Zlotowski matrix, and when you study your own model and try to study comparative statics, right? These are the calculus version of the revealed preference conditions that were imposed. So the GARP, the generalized axiom of revealed preference, and the weak axiom are the powerful, new tools that we understand and are easy and always works in finite or infinite data, right? GARP, when you make a differential, it will give you symmetry and negative semi-definiteness of the Zlotowski matrix. Surprisingly, the weak axiom is exactly the same as the negative semi-definiteness condition. And I will make that connection in a second. So this will be the role of the last part of the class. But before going there, let's take a very important step to now understand how can I use these nice conditions I derived on the Zlotowski matrix for something useful, right? So these are things that an econometrician can use to be able to test rationality, right? You can estimate your demand and then test that the Zlotowski matrix is symmetric. People have done it. There are published papers in Journal of Econometrics by Stefan Holderlein, for instance. He has tested rationality in market demands using the Zlotowski matrix. So these are useful in sound right by the stability conditions, but now we're going to use it also to be able to recover from demand the utility. Sorry, Martin, you have a question or any other questions here?
No, yeah, the relevant question between the axioms of revealed preferences and these implications of utility maximization is the difference between discrete and continuous, or the difference between the choice correspondence framework and the utility maximization framework on the other hand?
Yeah, that's a great question. That's a great question. It's really a difference between discrete and continuous. So when you have demand correspondences, of course, defining a Zlotowski matrix is very difficult, right? Of course, another benefit of the GARP on discreteness is that being a more modern, more powerful math, you can also deal with objects such as demand correspondence, right? So it can take us beyond what the Zlotowski matrix can do, okay? So, but the main difference is not that it's more general, allowing demand correspondences. It's really the difference between discreteness and continuous. In fact, they are the same object, right? It's just the kind of data you're studying. When you're observing a Zlotowski matrix, right, you're basically assuming infinite data. Remember this? So when you observe a derivative and you say you observe a derivative, basically what you're saying is that you're observing the changes in a small ball, right, of quantities, right, for any direction of changes of prices. So if you remember the notion of a directional derivative, right? So a derivative is in fact the collection of all directional derivatives in a whole open, ball, depending on the topology. So in fact, this means a knowledge of data that is amazing, right? It's basically that how quantities change for directional changes of prices in the whole possibility of directions, right? So this is knowing a Zlotowski matrix, right? The GARP instead allows us to just observe, discrete experiments with two prices and quantities. You cannot take derivatives here, right? And you can still say something about rationality. So it's way more powerful. But these are still useful, and econometricians use it because sometimes econometricians deal with functions instead of data points, right? Because the role of econometrics is to get from points, infer a function. Once you have the function, then you can take derivatives and so on. So again, due to historical reasons, people use this more, and we are better at calculus as humans than with discrete math. It's just, this is the case, right? We're just better, right? Since Newton, right? So now we're black belt at calculus. But with discrete math, we're still learning, right? So we're still, not there yet. And that's why this is still useful. But, I'm just telling you the historical perspective. In a way, these are rationality, but with tools from the past, right? And now, as we progress through the chapter, and this is not in Mascolel, I'm going to give you the more modern version with the GARP, okay? Okay,
Great.
but
yep.
Yeah, and but of course, one useful thing is this famous integrability. So what is integrability? So integrability is that we want, of course, to be sure that the symmetry, negative semi-definiteness, and singularity in prices of the Zlewski metrics are not only necessary conditions, has empirical implications, but also are all relevant empirical implications, okay? And how do I know it? The same as we did with the GARP in the previous chapters is by basically assuring that if I have a demand with an Zlewski matrix that is symmetric, negative, semi-definite, and singular in prices, those conditions are sufficient, right, to be able to get back a utility from the demand that is able to generate back the demand function from utility maximization. So this is, again, a connection with differential equations, right? So what is the role of differential equations? So basically you start with a function that is a derivative of something, right? And then you want to obtain the primitive function, right? From the derivatives, from knowledge of derivatives. That's essentially what differential equations are. Now, what are partial differential equations? Partial differential equations is getting back the original function from knowledge of partial derivatives. Do you agree? That's essentially what we're doing. This is a problem of integrability, right? So from knowledge of the derivatives, we want the original object, okay? So here, connection with previous lectures. Who remembers the Royce identity? I spent some time discussing. So the Royce identity basically link the indirect utility, right, through the gradients, right, to the demand function, okay? So essentially, the demand function is a derivative of the utility, okay? So in fact, it's a partial derivative. Each entry is a partial derivative of the utility. So we're gonna go from knowledge of partial derivatives, so hence the demand function. We're gonna try to recover the underlying indirect utility, and then finally the direct utility. Do you understand the job we're trying to do here, right? So from the demand to the utility. Any question here? No? Okay. So, again, here there is another reminder for the Zlewski metrics, theorem 9. So theorem 9, is another pinnacle of consumer theory. So all that you're seeing here are things that, were solved by, geniuses, mathematical geniuses. They were actually geniuses, right? So mathematicians were looking for something to do. They got tired of physics, they got into econ. Now they abandoned econ, by the way. They moved to computer science and, after moving briefly to biology. Now they're mainly computer science and machine learning. But, when they visit us, the geniuses in math, they gave us something like this, and this is a very nice term, Hurwitz, Usawa, and Richter. And it's basically the following, is assume that Walras law holds for my demand function. The Zlewski matrix associated with this demand is symmetric for LPW, okay? The Zlewski matrix is negative semi-definite. And of course, you have this, remember the Walras law implies the singularity of prices with symmetry. So that's why it's suppressed here. That's, I think I don't like about Mascolel because it makes a big deal about singularity of prices and now it disappears, right? Then you have to figure out that singularity of prices implies here by Walras law and symmetry, right? But whatever, I'm telling you, so put it on the margin if you want. And then, there exists and this is the key, this is the punchline. If that happens and you verify that, then there exists a continuous utility function differentiable that generates the data. That meaning that the demand function is the Rmax, so the result of maximizing the constructed utility from this utility subject to the budget constraint. Okay. Now, so this is of course very vague. So it's telling you there exists some utility. So some of you may remember the red flag about, existential claims or the axiom of choice, the non-constructive math, right? Now, however, in contrast to the statement, this is actually a sort of constructive argument. So we're going to use partial differential equation results to basically construct the utility from the demand. Okay, that's what we're going to do. Now, turns out, by the way, that the true proof of this is pages and pages and pages. I think last time I checked, a very nice proof collected by Kim Border, right, for a topics class. It was about possibly 2 pages, something like that. So it's very long and it's beyond the objective of the class. So nobody proves this. Western is no exception. You do it when you want to get into this. And also it's kind of an old topic. So we're not going to spend time on this. We're going to do a sketch. And then we're going to do an example with 2 goods, which is we're going to do it step by step, right? Which is more informative, right? And in fact, actually in previous years, and I'm going to do it also here, I discovered that it's easier to go first to the example and then just summarize it using the sketch of the proof. So let's go directly to the example, okay? So by the way, so people that are really, into math, don't worry, you can go and study partial differential equations and they're gonna tell you all about this. But all of these results are about before the 80s. So they are not new anymore. So the new thing now is the stochastic differential equations, and people use it for other stuff, right? So these team people have moved on in a way, right? It's a bit boring, but it still is useful, right? Even if it's boring. So we have 2 commodities, right? Simplest possible case, right? And now I'm going to propose the simplest possible demand, a Cobb-Douglas demand. So x1 of good 1 is equal to alpha, which is some coefficient between 0 and 1, times W divided by price of 1. So at this point, some of you may recognize this demand system because there are 2 goods as what? As being the demand system from maximizing a Cobb-Douglas. So who remember what is the utility from this Cobb-Douglas? What will be the utility from this Cobb-Douglas? Who can tell me from heart? Yeah, Simran?
X1 to the alpha and X2 to the 1 minus alpha, something like that.
Perfect. So it's a multiplicative utility, right? X1 to the power of alpha times X2 to the power of 1 minus alpha, right? Only in logs, it will be alpha log X1 plus 1 minus alpha log X2, okay? That's both are equivalent. Now, so maximizing this subject to a linear Apache constraint will give you the demand for X1, it will be alpha W divided by P1. In other words, right, you will always consume a fixed fraction of your income, right, equal to alpha, right? That would be the fixed purchase share, right? And then of course you have to multiply with what is affordable, W times P1. Now, of course, what would be the demand of good 2? The demand of good 2 will be 1 minus alpha W divided by P2, okay? You can check they satisfy Walras law because alpha plus 1 minus alpha is equal to 1 and so on. Now, furthermore, right? We have to check in this particular case, right, whether the conditions of the Slutsky matrix hold. So this is something, sometimes I do in class, sometimes I don't. This is something I'm going to ask you this time to do because I want you to practice. So take this Cobb-Douglas and compute its Slutsky matrix. So from computing this Slutsky matrix of the Cobb-Douglas, right, I want you to verify, and it's going to be in the problem set, by the way. I want you to verify that it is symmetric, negative semi-definite, and singular prices. So it's a bit of tedious calculation. It's not too tedious because it's a Cobb-Douglas, very nice to do, right? But at this stage, what I'm asking you to do, and we're assuming we're going to do, is that we have verified that the Slutsky matrix associated with the Cobb-Douglas demand system is 3 things: symmetric, negative semi-definite, and singular prices. Okay. Again, this is something easy to do. If you want to verify, you can Google it quickly, right? So the Slutsky matrix of the Cobb-Douglas is something that people do for training in undergrad. So that's why I'm assuming we have done it, right? Now, once you have done that and verified these things, now I'm going to do the following. So now I'm going to solve a system of partial differential equations. And of course, because we're in a class and we want to do things easier, we're going to simplify and make some tricks, use some tricks from the theory, right? To simplify our problem, and in fact, not to solve a partial differential equation problem, but just to solve an ordinary differential equation problem, okay? So in fact, because we have 2 dimensions, we're going to use the properties of our problem to make it lower dimensional. And one thing we are always going to use is because of Walras law and homogeneity of degree 0, after computing the Slutsky metrics, you can always, after computing the Slutsky metrics, this is a source of problem in problem sets, right? People do this simplification before doing the Slutsky metrics. After you do the Slutsky metrics and verify the properties, now you can fix the price of 2, or any price, in fact, to 1. And why you can do this? Because of the homogeneity of degree 0, okay? So namely, what you're doing is basically taking all your variables, right, and dividing by price of 2, okay? So the price of 1 becomes price of 1 divided by P2, price of 2 becomes 1, right? And basically the income also is divided by P2. So everything is measured in terms of income. Any questions here?
I have a question actually about this statement. Furthermore, we have checked that this demand satisfies warp, right? So it's after Slutsky, right? When we verify Slutsky, that the matrix is semi-definite symmetric, then we can say that this warp satisfied, correct?
Mm-hmm. So this is true. So warp implies, right, that the Slutsky matrix is negative semi-definite, okay? So in fact, I'm gonna check this thing, right? So here there are some connections. Of course, I'm following Mascolet here. So sometimes he's moving back from these things, which is not ideal. So furthermore, we have checked that this demand, right, has a Slutsky matrix, right? That is symmetric, negative semi-definite, right? And basically singular in prices. So as I discussed a moment ago, we're going to make connections with this with warp, right? And we know that warp implies negative semi-definite. I'm going to prove it to you in general. But right now, let's just go with the Slutsky matrix. I don't need you to process also these deviations from Mascolet, okay? So great question, Irina. So let's just move on using just the properties of the Slutsky matrix, okay? And then we make connections with warp. So now, we normalize after you have checked the Slutsky matrix. Now we normalize the price of 2 equal to 1. You can always do this, as I mentioned, because of homogeneity of degree 0. Okay, Walras law. Now that means after verifying the condition of the Slutsky matrix, you can always take one price and make it equal to 1. So we simplify a lot of the results in this particular case. And this is a trick you can always use when trying to do integrability. So now, what will be the demand of good 2? The demand of good 2 will be equal to 1 minus alpha times income. So what happened to the price? So price now is 1, right? So originally it was dividing, right? So the original demand was 1 minus alpha times W divided by P2. Do you understand, right? Now, because I have fixed price of 2 equal to 1, now this has been simplified. Okay, so what I'm gonna do is I'm gonna write now a differential equation from quantity 1, for quantity 1. And this is essentially going to do a small change. So I'm gonna take the original demand, x1, and instead of income, I'm gonna replace it by a function, which is a compensation function. So this is not in general an expenditure function right now, but we're gonna make it 1 in a bit. And then of course, we're gonna make it in fact an indirect utility. At this stage is an element of the proof. One in this example is an artifact in the example. And this function always works like this. We call it for now a compensation function, right? And it's a function of prices, right? So it just depends here on P1 and P2. And of course, P2 is fixed to 1. And as you can see here, we're gonna take the demand of X1 and we're gonna evaluate it at the new prices, P1, 1. We know that we have fixated price 2 to 1. And then this utility function that we have introduced now, of course, depends on P1, 1. Okay, again. And we're gonna write the following equation. We're gonna say that the derivative of this compensation function, the U prime, with respect to the only variable, P1, is equal to alpha of what? Of the income, right? This is the object I'm replacing. So mu of P1 divided by P1, okay? So what I'm saying, right, is I'm writing an ordinary differential equation where I'm saying that the demand I observe is the derivative of this compensation object, okay? So I'm saying mu prime with respect to the only argument, which is P1, is equal to alpha of mu P1 divided by P1, okay? So in other words, what I'm doing, right, is I'm taking the demand function, change the income or W by the mu function, right? And then equating this demand function to the derivative of this mu function, okay? So as you can imagine, this obviously relates to the Royce identity, but in particular, it actually relates to something we saw later, which is the Shepard's lemma. Who remembers the Shepard's lemma? The Shepard's lemma was telling me that if I take the partial derivative with respect to prices of expenditure, I get back what? The Hicksian, right? Do you remember that? So this is essentially doing that. So here I'm thinking, I'm transforming, if you want, the Marshallian demand into a Hicksian, right? Mu plays the role of the expenditure, right? And then I'm telling you the derivative of the expenditure is equal to the demand. Of course, the Marshallian demand now transforming in Hicksian by means of the indirect utility, right? Or the expenditure, which we know are inverses, okay? Do you understand this step?
Professor, I'm lost. I mean, really.
Yeah, don't worry. So remember, this was the contribution of Hurwitz and Osawa. So it's okay. So this is usually the step on the proof where you do something that's called guess and verify, right? So I'm proposing a construction out of the blue, right? So Hurwitz and Osawa say, I'm gonna write this thing, creating this mu out of the blue. This is my proof technique, right? So this is this how, you know, for you, it's gonna be almost an algorithm. So the way to understand it right now would be, okay, look, give me a demand. Okay, Cobb-Douglas demand. What do I do next? Compute the Zariski metrics, verify the conditions, 1, 2, 3. Okay, great. After that, if conditions are verified, take the entry 1 of the demand, right? Replace the income by a new function called mu, right? Okay. And now, right, equate the demand, evaluated at the replacement where W is equal to mu, equate that demand to the derivative of the mu. Okay, so now I just described steps, right? That's why maybe you're not understanding, right? Because all of these are just mechanical steps, right? Okay, so once you have done it, right, you are just establishing a problem we have to solve, right? This problem is called an ordinary differential equation, right? It's relating a derivative, right, with a function. So what is the derivative? Is in the left-hand side, mu prime. And what is the function? Is mu on the right-hand side, okay? And there are other variables there, alpha and P1. They work here as coefficients, so they can be thought as parameters that are fixed, right? And otherwise, is an ordinary differential equation, okay? So who remembers an ordinary differential equation from undergrad or master's or whatever, right? So this is one classical problem, right? The way to solve it is basically we basically want to write we want to put everything mu on one side, you know, and everything that doesn't have mu on the other side, right? This is one classical solution to these ordinary differential equations, right? Where we want to write basically the following. So we assume mu is non-zero, derive mu prime by mu, right? And leave the rest on the right-hand side. So on the right-hand side, I have alpha P1, and on the left-hand side, I have u prime divided by mu. Now, what is this important object here? Mu prime divided by mu. So if you derive the logarithm, what will you get? So you will get 1 by the argument, right? And if the argument is a function, then you will get in the numerator, the argument derived, right? By the chain rule. So for instance, derive logarithm of fx. So this will be 1 divided by fx, right? And then in the numerator will be f prime, right? So we're doing here the reverse operation. So we want to integrate back, right? So we take this object here, integrate back, and what do we get? We get logarithm of mu equal to what? The integral of alpha P1, right? Because this doesn't essentially, right? So is the same object as before, right? We integrate this 1 over P1. The integral is the logarithm, so it's alpha logarithm of P1, but there is a constant of integration. And the constant of integration is C, okay? So I just did the most basic solution of an ordinary differential equation. So the particulars of each solution to each ordinary differential equations are not important. In the case of Cobb-Douglas, this is the way to solve it, right? If you have gone through a book of ordinary differential equations, you know there are different kinds of differential equations, and each of them has some tricks to solve them. Do you understand, right? So the particular technique I'm using here is not essential, right? It's only the appropriate one or easy one for the Cobb-Douglas case, okay? You don't have to use it always, okay? Now, once you have done it, right, you obtain now, you solve for mu, which is the object of interest. And now, in order to solve for mu, I need to exponentiate, right? The inverse mapping of the logarithm. So now I apply an exponential mapping. Applying an exponential mapping will give me mu equal to k, a new constant, which is equal to the exponential of the constant of integration c, times p1 to the power of alpha. So now Sebren, as he told us, remember that the Cobb-Douglas was x1 to the power of alpha times x2 to the power of 1 minus alpha, right? So here you have something that looks like a little bit like the Cobb-Douglas, right? You have x1 to the alpha. But it's still not there. So how do we get there, right? So after you obtain this mu function, which is the creation of the mind of Hurwitz-Osawa, right? Then they proceed to use the mu to obtain the direct utility. So the magic trick that follows is going to be get this mu I created, and from this, get the Cobb-Douglas that Sebren told us, okay? So let me keep going. All of this is just steps, right? So we're gonna get back and then I'm gonna do the sketch of the proof. So don't be afraid if you're getting lost. This is complex. Again, Hurwitz-Osawa did it 3 pages. They got an econometric there. It's kind of a big deal. What I'm gonna do is the following. So remember this object mu, right, works essentially like an indirect utility / expenditure function. We know they are inverses, right? So at this particular stage, this actually for me, it is more an expenditure function. The name doesn't matter. We have solved for mu. This object is still not a direct utility. Why? Because I have to be able to allow for income changes, right? So here I just allow price changes. So I have to be able to understand how this changes with income. So what we're gonna do is the following. So I have this constant of integration k that obviously has to be related to the income level, right? So the income level so far we haven't paid attention to it. But remember that the original demand that we were given with the Cobb-Douglas has an income level, right? This is a particular number. So now we're gonna fix the price that is not fixed, the P1, and the income level to some particular number. So you can think of P10 as, for instance, the number 2, and the W0, it can be number 10. So this is an arbitrary number you pick, an arbitrary price of good 1 and an arbitrary income level. So when I add to this the superscript 0, it just means that I move from variables to numbers, okay? So given some initial conditions, so numbers of P1 and W, now let me solve for K. So now notice the following. Remember the mu was replacing the role of income. That was my step, initial step, right? So now let me fix the income level W0 and equate it to the solution here. K times P10, a new number, right? To the alpha. And then solve for K. Once you solve for K, now you get a number, right? Alpha is a number, W0 is a number, P10 is a number. So now K became a number. Okay, great. That's what you do in integration, right? So you remember your classes of calculus, right? Once you have obtained the integral up to a constant of integration, you find some initial conditions, and using the initial conditions, you obtain the constant of integration, right? Do you understand? So this constant of integration, of course, changes for the choices of prices and income. Everyone with me? Good. Now, so this tells me something fun. Look, this mu, right, was a function of prices, right? but it depends on a constant of integration that depends on the initial conditions P1 naught and W naught, okay? So in fact, there's going to be a different constant of integration if I choose different P1 naught and W naught. Do you understand? So instead, in fact, you know, K changes with prices and income, okay? So secret, K here is in fact the object we want, because this object here, right, is gonna be basically indexing the changes in prices and income. So we're gonna use it now, right, to write down finally a proper indirect utility. How we're gonna do it? So look at this magical step where we notice that the mu, right, has the variable, right, because it's a function of P1, and then it depends on the initial conditions I choose, P1 naught, W naught, right? So at this stage, everyone is with me, right? I have replaced K by W naught, P1 naught to the alpha, and then P1 is just the variable, right? So P1 to the alpha. Nothing fancy here. This is just calculus. Now is the conceptual part. Because this object here changes with initial conditions, right? I'm now gonna fix the variables. I'm gonna fix the first P1, and that's why it has a star on it. So now I'm gonna fix it for any price I want, right? So imagine I fix it for price equal to 3. So P1 star now becomes 3 and it's fixed. And now I'm gonna allow P1 naught and W naught to change, okay? So I'm just gonna let K to change, okay? So K is gonna be moving around now, okay? So I move the P1 now and I'm gonna allow K to change, okay? Hence, I'm gonna change the initial conditions. Again, why you may not understand this step? Because comes from Kurogane-Izusawa brain, right? So they are doing this and they are gonna show us that this is in fact is gonna produce a direct utility that if you maximize, it's gonna generate the utility maximization. So it's part of a proof, right? So they provide then to us an algorithm that we can follow that is not easy to figure out why it works, right? So that's why it comes a little bit out of the blue, because in fact, it's from the brain of two mathematicians, right? This is what mathematicians do. They guess and verify. So these are guesses. It turns out they work, right? So don't be afraid if you don't know where this comes from, right? This is the trick that comes from Kurogane-Izusawa. Because they did the trick, now we know them and respect them, right? That they come up with that trick, right? So this comes from their mind. Of course, they may have some inspiration, but it's a little bit like poetry, right? Why they did a verse like that, right? That rhymes so nicely. Well, I don't know, I cannot explain. It comes from their brain, right? They may have some really cool experience or traumatic experience, who knows, right? But you know, their brain produces them, right? This is a little bit like that, right? So don't be afraid that you don't know where this comes from, right? We're gonna learn those steps and then use them, right? That's our role right now, right? And these steps basically are telling me that once I have obtained the mu, and once I have solved the initial condition K by changing the initial conditions P1 naught and W naught, then I'm gonna flip roles. I'm gonna fix the variable P1 and then use the initial conditions and change it, okay? So this is the step called role inversion, okay? Once you have done it, now you declare the candidate indirect utility B of P1W to be the mu at any fixed price level P1 star for the variable P1W that were the initial conditions, okay? Do you understand? So now let's do it, right? So in particular, I'm gonna fix the P1 star in this proof for elegance to 1. It can be any other number, okay? Are you aware of that? It can be any number, like 1, 3, 10, 100. I'm gonna fix it for elegance to 1. Now, this gives me an indirect utility that depends only on P1 and W. And let's go back to this expression here. Replace P1 star by 1. What happens with this term? It becomes 1, right? So out of the picture. And this object here is just W divided by P1 to the alpha. Okay, so now, you know, the claim of Kurogane-Izusawa is that this is the indirect utility of the Cobb-Douglas. Okay, but how I'm sure, right? I'm still not done. Now, you know, if this is in fact the indirect utility of a Cobb-Douglas, it must be the case that if I replace, you know, the inverse demand, and what is an inverse demand? The inverse demand is essentially this object here that is mapping prices as a function of quantities, right? And income as a function of quantities. So this is the result of inverting the Cobb-Douglas demand. So if I replace the inverse demand in the indirect utility, it has to give me back the direct utility, okay? By definition, right? Because the indirect utility is expressed in P and W. If I invert demand, it's going to be a mapping from prices and income to quantities, X1, X2, right? If I replace the inverse demand, right, inside the indirect utility, it has to give me back the direct utility, okay? Games with inversions, right? Easy. Now, bear with me. I know it's long, I know it's hard, but we're almost there. So what do? Take the Cobb-Douglas demand, right? Invert it. What does it mean inverting? Solving for P1. So X1 is expressed as alpha times W divided by P1. Solve for X1, for P1, sorry. What do I get? I get alpha divided by 1 minus alpha times X2 over X1. Then go to the demand of good 2 and solve for W. W is equal to X2, 1 minus alpha. Okay, again, formally. What is an inverse demand? Inverse demand is a mapping, right, from quantities to P and W, right? So I'm just inverting the role of things, right? So the inputs are X's and the outputs are P and W, right? The usual demand is inputs are P and W, outputs are X's, right? Okay, so the inverse demand is reverting the roles, right? So now in this particular case, I obtain the inverse demand of the Cobb-Douglas. So the inverse demand is P1 is equal to alpha divided by 1 minus alpha, X2 over X1, and W is equal to X2, 1 minus alpha. So let's do the final magic trick step, right? The final step of this magic trick. So take the indirect utility above, right? The one I just wrote here, and replace for the indirect demand. So in particular, this is W divided by P1 to the alpha. So in the numerator, it would be the expression for W. What is the expression for W? Is X2 divided by 1 minus alpha. Okay, everyone with me? So numerator will be X1 divided by 1 minus alpha. Okay, what is the denominator? Is P1 to the alpha. Okay, what is the expression for P1? Is this long expression, alpha divided by 1 minus alpha times X2 divided by X1. Replace that in the denominator, right? Everyone with me? Then, you know, algebraic magic, tricks with algebra, just rearrange terms, and now I get the following. I get X1 to the alpha, X2 to the 1 minus alpha, plus constants. And these constants, they're going to be collected into C hat, which is essentially 1 minus alpha to the alpha, alpha to the alpha. Well, Severin may not be completely happy because we just got X1 to the alpha, X2, 1 minus alpha, and we get some naughty terms around, right? Those naughty terms, do they matter? Not really, right? Because the utility function, we know its content is ordinal, right? So any scaling up, such as alpha, 1 minus alpha, alpha to the alpha, alpha, doesn't matter, right? It can be as well any other term. This particular C hat is the result of the normalization choices we have done. Like the P1 star that we chose it to be equal to 1, all of this is here, right? If I chose it to be equal to 1,000, it would change my object C hat. Does it matter? Not really, okay? This is the whole Hurwitz-Zusawa magic trick. It's really cool, right? Now, what is the output of the object? So give me a demand function, check the Slutsky matrix conditions. They are passed. Now I'm allowed to do the Hurwitz-Zusawa magic. Because I'm allowed to do the Hurwitz-Zusawa magic, I'm able to obtain a utility function from the demand. So why this is useful? So of course, we know that the Cobb-Douglas has a Cobb-Douglas demand, so it's kind of silly, it's for a class. In real life, you estimate a demand function, right? You don't know if it's rational or not. So first of all, check your Slutsky conditions. If you check it's rational, then what would be an interesting question to ask with the demand function? Welfare questions, right? So for instance, what would be the welfare change of this consumer if I change my prices from this level to a new level, say, put a tax on sugar of 10%, right? If I put a tax of sugar of 10%, what will be the welfare change? How do you know the welfare change? You need a utility, right? How do you know the utility? You need to do integrability, okay? So this is essentially what people do. So a lot of people are hired in the World Bank. I was hired by the World Bank because I was younger, right? I worked as a consultant. And, you know, also for European Union. So they have some missions here in Latin America. And one key question was, you know, welfare changes for tax reforms, right? Also for cash transfers. For instance, how much will it change the welfare of households if you give them a cash transfer? Or how much will their welfare change if you put taxes on food, right? So a lot of developing countries, they rely on indirect taxes. What are indirect taxes? Are taxes on sales, right? If you put taxes on sales, there's a lot of substitution patterns and so on. Okay, so you're going to estimate a demand system, like the almost ideal demand system. Once you obtain that, you're going to do some integrability magic to be able to obtain back a utility function. Once you have that utility function, you do welfare analysis, okay? So actually this is useful. People use it, make money out of it, make policy out of it. This is an important thing, okay? Now, how to do it well, that's another thing, right? This is an important problem, but it's also very hard. And so we have done the very toy version model, right? So this is very, very low level, right? It's like in martial arts, you started with a, with a typical, punches there, very basic, this is that level. Imagine in real life, how many goods you usually have in a survey. So if you're studying food, at a very granular level, it can be hundreds of goods, right? So some surveys now in developing countries even are very granular. For instance, you have the difference between white rice and brown rice, right? So it's very fine. If you have all those goods, your demand system can be potentially huge. Once you estimate this and verify this still makes sense as a rational object, then you have to integrate that object. That means you have a huge partial differential equation system, right? Solving that analytically by hand, nobody can do it, right? So what do people do? They do numerical solutions of this integral problem, right? Or they use a demand system, which is nicer to integrate, such as the almost ideal demand system, that you're a little bit or a causing of that, which is part of your problem set, right? So a little bit of one of the questions in your problem set is going to be about playing with that, okay? With trying to deal with demand systems that are easier to integrate. Okay, so all of this is an art, obviously. So this is another rabbit hole. Some people make a career out of demand system estimation and integrability, one of them being Deaton, right? That won the Nobel Prize because of these efforts, right? And other things. So this in itself is a rabbit hole. Now, are you done with this? Obviously not. You need a problem set. I'm going to send you a problem for you to practice this thing. Okay, in the last 15 minutes, and it's going to be very simple again. Two goods, right? And then you have to integrate back. Okay, in real life, if you get into this, you have to do numerical integration and numerical solutions of partial differential equations. Okay, but let's summarize what we did with a sketch of the proof. And then let's see how it connects with the symmetry of the Zariski metrics. Because if you realize what I did, where did I use the symmetry of the Zariski metrics? So you have to be suspicious, right? What's going on with the Zariski metrics, right? And I'm going to tell you in the sketch, and I'm going to explain in the closing of this lecture. So the sketch of the proof that essentially says that if you have a demand system that has the three properties of the Zariski, symmetry, negative semi-indefiniteness, and singularity in prices, then you can construct a utility function. So the way to do it is by, a constructive utility using the solution of partial differential equation system. So the way, Hurwitz-Usawa proceed is by proposing this canonical problem, which comes from their mind, which is that the partial derivative of this introduced object, mu, that is a function of prices with respect to the price I, this is one of the L prices, is equal to the I quantity evaluated instead of income at the mu function at a price T, okay? So this is a partial differential equation system, right? How many of them do I have? L partial differential equations, because there are L prices, okay? Now, remember that income is changing. So how do I relate with income? Well, I have to know that if I evaluate this function mu, the value of the function mu at the price naught, so any fixed price I choose, then it will give me back the original income level, W naught, right? And these are the initial conditions, okay? Then remember, I can then flip the solution to this thing and then use the initial conditions as the variables, right? And using that, I can propose the indirect utility. Importantly, where do I use symmetry of the Zariski metrics? Look at this, step 2. Use the solution to the partial differential equation system in step 1. Define a candidate indirect utility. A solution exists if the Zariski matrix is symmetric, right? So the partial differential equation, we just solved it, right, magically in our example. But the solution is not guaranteed to exist, right? If you're solving a 100 good system, using numerical methods, how are you sure this thing even exists, right? And you're getting just trash out of your algorithm, right? Computers may give you trash, right? Trash in, trash out. How are you sure that your 100 good system of different partial differential equations have a solution at all, right? You don't know. You have to use this theorem. If the Zalewski matrix is symmetric, then you're assured to have a solution, okay? That's the importance of symmetry. Symmetry gives you existence of the partial differential equation system, okay? That's why it was hidden in our example, because the solution was there, right, for us to pick, okay? Now, if there is no symmetry, no solution, okay? Good. Second thing, using this mu function, I invert the roles, right, such that the initial conditions become the variables, and I propose a candidate indirect utility, okay? Using the indirect utility, I use the duality magic to basically define the expenditure function, right? And basically, I'm able to do this. And then, important thing, where does the negative semi-definite enters, right, in this work? Well, negative semi-definite restriction on the Zalewski matrix basically tells me that the BPW is homogeneous of degree 0, right? And quasi-convex, okay? So remember what was the counterpart of this for the expenditure function? That the expenditure function is homogeneous of degree 1, right? And concave. Okay, you can go back in the lectures and check these properties. I know them already by heart. You will learn them for this class, right? Then possibly you will use it if you become this particular field, right? But you know, this is something you have to remember for the class. Now, that means negative semi-definiteness allows me to have a well-defined indirect utility. It has the properties I need. So in other words, it will be a quasi-convex indirect utility with a counterpart expenditure that is concave. What was the importance of the concavity of the expenditure function? The importance was, you know, that it gave you that the Zalewski matrix was negative semi-definiteness, negative semi-definite. And this is essentially the weak axiom of revealed preference, right? So you're imposing the weak axiom through this negative semi-definiteness, right? And now, of course, the symmetry that allows this thing to exist was giving me the extra part that I need to complete the weak axiom and make it a generous axiom, right? So these are one and the same object, right? And the way to use it is essentially using symmetry to allow existence of the partial differential equation and negative semi-definiteness for basically providing shape restrictions on the solution to this problem. So the BPW, which is the solution, right, will be quasi-convex. So it won't be an arbitrary thing that can be wiggling around. It will be quasi-convex, right, which we know is the mirror image of a concave expenditure function. So basically, negative semi-definiteness is buying us that the solution to the differential equation system is going to be a concave solution, right, in the space of expenditures. Understood? Okay. And finally, I obtain the direct utility by using the inversion of my demand and obtaining the indirect demand. The indirect demand, remember, is this object that maps excess to P and W, okay? By replacing this in the indirect utility, which is a function of P and W, gives me back the direct utility. Now, important thing for you to know, this Hurwitz-Usawa, even if Mascolet doesn't say so, is obviously assuming invertibility of demand, okay? Important question for you, is every demand invertible, okay? So think about this for the next class. If you have an example that of the demand system that is not invertible, you know, you can get some extra points in the next midterm, not midterm, in the next problem set, right? So just say 2 points, okay? So again, it's just for you. So think about it, right? So try to create a demand system that is not invertible. Of course, the easier would be at two goods, right? 2 goods example. I don't think with 1 good it will be easier to do. Essentially, you know, remember you live in the positive world and so on, okay? Now, so try to do it for 2 goods, also not trivial. So try to create a demand system not invertible. So Hurwitz-Usawa assumes invertibility of demand. Okay, short story. Now you obtain finally a direct utility. Okay, so here, you know, we're gonna stop the recording. So let me stop it and then we can ask questions.